So what do you wanna, like, personally accomplish with liquid crystals, would you
Yes.
say? Like, what are your ambitions? Because, I mean, obviously, we already have the LCD
Uh,
screen, like, what are your thoughts that you can accomplish by mastering the technologies? Like
So these liquid crystals we've known for a while. They're called passive liquid crystals, right? You make them in a lab, make them in a factory. But in the past 10 years, people have started to get a lot more interested in what's called active liquid crystals. And there's this whole field called active matter. It's closely related to soft matter. But active matter is just a type of matter where you apply some sort of energy. It could be something simple like you shine light on it. And it takes the energy and it turns it into movement, right? So this is a very broad category of materials, but cells are active matter, right?
yeah.
Plants, right? But we can think about inanimate active matter as well. So they're active liquid crystals. So if you shine light on them, they start to wiggle a little bit, right? And you can direct that into a certain type of motion. So what I'm interested in is how can we use this, exploit this to maybe do some kind of computation, right?
Mhm.
Because clearly there's information stored in the direction of the field, right? So the direction of these rods, they can change from point to point. And the idea is based on that structure, you store a bit, for example, and you move those around, right? You apply some sort of light or electric fields, right? And you compute things, right? If we can do this with the displays, right? In principle, it should be possible with active liquid crystals to do some kind of computation.
So you go, like, this is like quantum level, so to speak, like, you in terms of, like, possibilities of beating the current state of computing.
Yeah, so there's a lot going on here, but it's not quantum, right? And we can talk about quantum computing,
We
but it's
will,
not,
yeah.
but it's not quantum. So it's actually still classical computing, right? And the reason is, if we talk about quantum computing, we're isolating one or a few atoms or electrons, and we're making it very cold around the atom so that it retains its quantum mechanical properties, right? But ordinary matter, we don't see those quantum effects for the most part because you got a whole bunch of atoms or electrons interacting with each other. So at the level at which I'm talking about liquid crystals, we don't really care too much about the quantum effects. So we're not using quantum effects in the screen. It's mostly classical physics. And quantum mechanics is really important in physics, of course, but there are a lot of people studying classical stuff too, right? So when I say classical, I mean these things are at room temperature,
Yeah.
right? But that doesn't mean they're not complicated. They're insanely complicated, and in some sense, they're actually a lot more complicated than quantum stuff, right?
Mm.
Quantum stuff is unintuitive and freaky, but the classical physics stuff, the mathematics is just insane. Like it's unsolvable as far as we know, right?
Mm.
But this would be a way to do computation that's in some ways like a classical computer, not too much like a quantum computer. But in any case, I might want to say this is sort of like a third way of computing,
Right.
right?
What kind of because again, most of the things that you're explaining to me, because you're explaining well, I do understand. I will say probably 60% max of
Sure.
complexity, to be fair. And
Let's get it to 100%.
like, what kind of products can you imagine getting out of that third way of computing? Like, what happens in our daily lives if at some point? Because the way I look at this is like if everyone starts getting excited about the same things, you're describing to me, and I'm getting excited with no technical background, with no physics background. But if everyone gets there, things are going fast in terms of
Mhm.
improving our lives as laymen's, so to speak.
Sure.
Like what do you imagine happens if we get to that kind of excitement and using that third way of computing that you just
Sure.
mentioned? What happens?
Sure. Let me give you two examples of what we might be able to do with this. So there's something called colloidal robots,
Yeah.
right? So a colloid is just a tiny particle, right? And I'm not talking about an atom. It's much bigger than that. But a particle that's small enough that you typically can't see it with your naked eye. But if you get an ordinary microscope, light microscope, you'll probably be able to see it, right? So examples are milk. So it looks continuous, smooth. But if you zoom in, there's little fat droplets that are floating around, right? But they're small enough that they just move around randomly because of they're getting bumped by these other atoms in the liquid. But they're light enough that they don't settle down, right? So they're in perpetual motion, basically. And another example would be paint. Again, looks continuous, but they're tiny particles embedded in there. So colloidal robots are robots that would be that size, basically,
Mm.
right? They're microscopic, but they're light enough that they just kind of float around, right? So liquid crystals play a role here. So, for example, there's some research that was done a couple of years ago where these experimental physicists, they get this 2D plane of liquid crystals and they stick this tiny piece of metal in there. And it's not a robot in the traditional sense, right? There aren't any electronics inside of it. It's
Yeah.
literally just a hunk of metal. But on the outside, you've got this magnetic or electric field that's controlling this thing. So it's not touching it, but kind of remotely moving it around, right? But remember that these liquid crystals, they have rods, and the orientation is different in different parts, right? So the setup is you have this chunk of metal, and it's shaped like a plus sign, let's say, right? And you've got these little colloid particles. So in the experiment, they used silica. So it's, you got these silica packets like gel that you have in food to preserve it. It's exactly those things.
Okay.
So these little balls, right? You stick them in the liquid crystal, and you got these little pieces of metal that we call robots. But again, there's nothing inside of them. But liquid crystals, when they're on some surface, they like to stand perpendicular to the surface, right? So they made this plus-shaped robot so that the liquid crystal lines up around it. And you can tell how, based on the way it's lined up, it's creating this distortion in the field, right? So we use this magnetic field to move the little piece of metal around, and that creates this big distortion that gets propagated throughout the rest of the field. And you got these little silica particles over here, and that distortion controls the flow of the whole fluid. So you rotate the little robot, it creates this ripple that drags the little particle to the other side, for example. And they can control this so precisely that they can bring a few particles from here and stack them to make a shape arbitrarily. Right? And again, I just want to emphasize these things are tiny. So this little piece of metal, they're able to arbitrarily stack complicated shapes and not disturb it, right? So that's one kind of immediate example. And you can imagine how you could use that to make more complicated displays, or even just to transport tiny particles, right? Imagine a tiny little device that's doing something related to medical applications, right?
Yeah.
So that's kind of an immediate application. But let me give you a super far out, just 50 years from now application, which is people have started to find out that if you look at certain living organisms, the orientation of those rods determines how it grows, right? So liquid crystals are found in many places, not just TVs, but inside of you. So you're made of cells, and those cells are made of membranes. Those are liquid crystals. Right? If I have a cell membrane, those particles can be modeled as rods. So if I push towards the membrane, perpendicular, it acts sort of like a solid. Right? If I poke it, it doesn't collapse. But if I'm in the plane of the membrane, right? If I'm swimming there, and I look to my neighbors, you're floating around like a liquid. Right? So the rods are constantly changing positions, but they're all oriented the same way. So that's one place you see liquid crystals. But a really interesting place that people have found liquid crystals is hydra. So it's this sponge-like animal, right? And it kind of grows like a tree, sort of. And people have found that there's these things called defects. So the rods, they're all oriented a certain way, but you can imagine that at some point they have to change direction. And if you have many different rods aligning like this, then in the center, you get this singularity. There's a unique direction. Right? So just imagine like a clock, right? The hands, you can imagine those as rods, but in the center, there's no unique direction. Right? Turns out that those points are places where you have extra cell growth or less cell growth. Based on that, the hydra is able to grow an arm or not grow an arm, right? So, of course, deep down, the DNA has some sort of information that's telling the hydra how it's going to grow, but nobody knows right now how that information gets to the actual morphology of the animal.
Yeah. That's just new matter coming and
Yeah, so the idea is, for example, when you're just an embryo, you're just a single cell. You start dividing, and now you're 2 cells, 16 cells, 32, right? But you're just a ball. At a certain point, though, some cells die, some cells grow in a certain direction. You get an arm or a tail, gills, whatever, right? How do those cells know that?
Yeah.
Right? How does this cell know that it needs to die versus this cell realizing that it needs to divide more?
Yeah.
But people have started to found possibly liquid crystals convey that information to all the cells.
Will it be the same, like, for example, even the human body in the sense that, like, I don't know, my fingers know when to stop growing, or
Exactly.
like, there's,
Right.
like,
Yeah.
hair or whatever, like, at some point knows when to stop and knows how to start, like,
Uh-huh.
and that's how you will basically use that, like, computational power and, like, to...
Yeah. So to get into that, this is a crazy idea, but I think one day it could happen. So plants, for example, are just amazing because you just plant it in any direction you want, and it knows to fight gravity and go the other direction. So some people, they'll put a plant on a plate and they'll spin it really slowly, and the plant will grow in a spiral, right? And you could plant it sideways, for example, and it's gonna learn to grow this way, right? We've all seen this. So somehow, somewhere in the DNA, it's telling the plant something about its environment, right? And somehow from the DNA to the outside of the plant, it's figuring out how to bend. Again, nobody really knows how this works, right? But maybe liquid crystals provide some sort of in-between mechanism to convey that information to the other cells. That's kind of the thought process right now. So if you think about it, it's amazing because plants have this blueprint for what they're going to build. Okay, so they spend all this time on smart houses, right? And building a house is not easy, right? Even just a dumb house, right? There's all these problems. It takes months, right? But what if you could just plant a house?
Yeah.
Right? So you create some cells that have some blueprint for that, what the house is going to be like. And think about, a lot of houses, especially in Japan, they're made of wood. Okay, so you just grow them on the perimeter, and you've engineered some blueprint into them, and you just give them some sunshine, and it doesn't matter if it's windy or rainy or whatever. The thing just grows up straight,
right.
and it finishes, right? I mean, that's what your body does, right? Your body knows that, it creates this hand, and then it kills these specific cells so you don't get webbed fingers, for example.
Yeah.
Right? How does it know that?
How this is crazy stuff.
Yeah.